Today we will be discussing electromagnetic induction, which is physics of class 12th, course 3 and unit 4 of the book, module 1. What is electromagnetic induction? We have seen in earlier chapters that moving charges produce magnetic field. Like a current carrying wire can deflect a magnetic compass. A very obvious question that comes to our mind is that whether the reverse is also true. That is, can a moving magnet or a changing magnetic field also produce electric current? The answer is a resounding yes. The experiments of Michael Faraday in UK and Joseph Henry in USA established in the year 1830 that electric currents were induced in closed coils when subjected to changing magnetic fields. The phenomenon in which electric current is generated by varying magnetic fields is called electromagnetic induction. The phenomenon of electromagnetic induction is the basis of working of generators, dynamos, transformers, etc. And these devices form the basis of production and distribution of electricity. And we cannot imagine our world without electricity. And hence, the concept of electromagnetic induction is of utmost importance. We shall now discuss some of the experiments carried out by Faraday and Henry. Experiment 1. Current induced by a magnet. Let us take a coil C1 connected to a galvanometer G as shown in the figure. Normally, in such a setup, the meter would not deflect as there is no source of EMF. We have taken a coil which is attached to the galvanometer. We also have a bar magnet which can be moved in and out of the coil. We observe that when the north pole of a bar magnet is pushed towards the coil, the pointer in the galvanometer deflects, indicating the presence of electric current in the coil. The deflection lasts as long as the bar magnet is in motion. The galvanometer does not show any deflection when the magnet is held stationary. Now, when the magnet is pulled away from the coil, the galvanometer shows deflection in the opposite direction, which indicates the reversal of the current's direction. When the south pole of the same bar magnet is moved towards or away from the coil, the deflections in the galvanometer are opposite to that observed with the north pole for similar movements. The deflection and hence current is found to be larger when the magnet is pushed towards or pulled away from the coil faster. When the bar magnet is held fixed and the coil C1 is moving towards or away from the magnet, the same effects are observed. So, we can conclude that it is the relative motion between the magnet and the coil that is responsible for the generation or induction of the electric current in the coil. Let us move on to the next experiment. Experiment 2. Current induced by current. The bar magnet is replaced by a second coil C2 connected to a battery. The steady current in the coil C2 produces a steady magnetic field. As the coil C2 is moved towards the coil C1, the galvanometer shows a deflection. This indicates that electric current is induced in the coil C1. Now, when C2 is moving away, the galvanometer shows a deflection again, but this time in the opposite direction. The deflection lasts as long as coil C2 is in motion. When the coil C2 is held fixed and C1 is moved, the same effects are observed. Again, we can conclude that it is the relative motion between the coil and that induces the electric current. Let us look at the third experiment, in which there is no relative motion. Two coils C1 and C2 held stationary. Coil C1 is connected to galvanometer G, while second coil C2 is connected to a battery through a tapping key K. We observe that the galvanometer shows a momentary deflection when the tapping key K is pressed. Now, if the key is held pressed continuously, there is no deflection in the galvanometer. When the key is released, a momentary deflection is observed again, but in the opposite direction. The deflection increases dramatically when an iron rod is inserted into the coils along their axis. Through this experiment, it can be concluded that relative motion is not the absolute requirement for induction. Current can be induced by changing the current in the neighboring coil. Now, to understand the Faraday's experiments mathematically, let us first understand the term magnetic flux. Magnetic flux, just like electric flux, is the number of magnetic lines of forces crossing a given area held perpendicularly to the magnetic field B. Mathematically, it is equal to the dot product of B and A. Hence, magnetic flux is a scalar quantity. Phi B is equal to B vector dot A vector, which is BA cos theta, where theta is the angle between magnetic field B and area vector A. As can be seen in the diagram, flux phi is equal to B dot A, which is again equal to BA if area is perpendicular to the magnetic field. If area is perpendicular, that means the area vector is parallel to the magnetic field, or theta is 0 and cos 0 is 1. If area is not perpendicular, then phi is given by the product of component of the magnetic field perpendicular to the given area and magnitude of area vector. The other aspects of magnetic flux are: flux is proportional to the number of magnetic lines of force through a unit perpendicular area, that is, the strength of the magnetic field. Flux varies with the angle between B vector and A vector. Flux is also proportional to the area. So, mathematically, when the surface is parallel to the magnetic field, then the area vector will be perpendicular to the magnetic field and theta will be equal to 90 degree. So, phi will be equal to BA cos 90, which is equal to 0. When surface is perpendicular to the magnetic field, then area vector will be parallel to the magnetic field and theta will be equal to 0. So, phi will be equal to BA cos 0, which is equal to BA and is the maximum value of the flux. When a coil of N turns, each of area A is held in a magnetic field of strength B. Magnetic flux associated with the coil is given by phi B equal to N times B dot A, which is equal to NBA cos theta, where theta is the angle between the direction of B and normal to the surface area of the coil, which is the area vector. Coming to the unit of magnetic flux, the SI unit of magnetic flux is Weber or Tesla meter square. 1 Weber is defined as the amount of magnetic flux over an area of 1 meter square held normal to the uniform magnetic field of 1 Tesla. The CGS unit of magnetic flux is Maxwell, where 1 Weber is equal to 10 to the power of 8 Maxwell. Cause of induced EMF. Having understood the concept of magnetic flux, we can talk about the cause of induced EMF in context with the Faraday's experiments. We concluded in experiments 1 and 2 that it is a relative motion between the coil and the magnet or between two coils that induces a current in the coil. The question is why? What happens when there is a relative motion between the two or when there is no relative motion between them? The answer lies with magnetic flux. Whenever there is a relative motion, the number of lines of forces associated with the coil changes. That is, the magnetic flux associated with the coil changes and a current is induced in the coil. Experiment 3 has a slightly different story. As the key is pressed or released, the current in the second coil and hence the magnetic field associated with it increases or decreases in a short interval of time. Consequently, the magnetic flux through the neighboring coil C1 also increases or decreases in a short interval of time, thus inducing a current in it without any relative motion between the two coils. From the above observation, we can conclude that the time rate of change of magnetic flux through a circuit induces EMF in it. Faraday stated experimental observations in the form of laws called Faraday's laws of electromagnetic induction. Faraday's laws can be stated as follows. First law states that whenever the amount of magnetic flux linked with the coil changes, an EMF is induced in the coil. The induced EMF lasts in the coil so long as the change in the magnetic flux continues. Second law states that the magnitude of the EMF induced in the coil is directly proportional to the rate of change of magnetic flux linked with the coil. Regarding first law, we observe that if the key is kept pressed or magnet is not moving, no EMF is induced. Hence, the induced EMF lasts in the coil so long as the change in the magnetic flux continues. If there is no change in the magnetic flux, then there will be no EMF that will be induced. The second law can be concluded from the observation that when the magnet or the current carrying coil was moved at a faster rate towards or away from the coil C1, the galvanometer shows deflection. So, mathematically the induced EMF is given by E is equal to minus d phi b by dt. The negative sign indicates the direction of E and hence the direction of current in a closed loop. In the case of a closely wound coil of n turns, change of flux associated with each turn is the same. Therefore, the expression for the total induced EMF is given by E is equal to minus n d phi b by dt. Direction of the induced EMF. E is equal to minus d phi b by dt. The negative sign is taken because induced EMF opposes any change in the magnetic flux associated with the circuit. This follows from the Lenz's law, which we will be discussing in module 2. Thank you.